This section explains why a book's zeroth chapter matters. A book's zeroth chapter is not content, but substrate, the invariant vocabulary every later construction silently assumes. Two things are collected: the language of sets and maps, and the arithmetic of the integers, meaning divisibility, greatest common divisor. The one generative primitive worth extracting is proposition 2. An equivalence, relation, and a partition are the same object seen twice. To quotient a set is to collapse it along a relation, which is to slice it into disjoint classes, one act, two descriptions. Every quotient the book later builds, cosets, quotient groups, quotient rings, is this single move re-instantiated? Fibers of a map are its first appearance. A map F partitions its domain by equal image. Master the collapse here and predict all of them. This section explains how one structural move sits beneath everything the book will later call a quotient. Everything the book later calls a quotient is already here, stripped of algebra. An equivalence relation shatters a set into disjoint classes. A function's fibers, the pre-images written F inverse of B, are exactly that partition indexed by the image. So, collapsing a set by sameness and reading a map by what it identifies are one move, the move every quotient, group, ring, and module will rerun. Bijection is its degenerate case, all fibers, singletons, nothing collapsed. It is the seed that structure preservation later sharpens into isomorphism. The integers enter omi to give this skeleton its first flesh. Division and greatest common divisor are where the abstract partition first computes. This section introduces what a group is and why 3 axioms are enough to capture the idea of undoing an action. 3 axioms are all it takes to name what it means to undo something. A group is a set closed under one associative operation, carrying a do-nothing element and, for every element, an exact reversal. It is the abstraction of invertible action composing with itself. The chapter's move is to see that the integers under addition, the non-zero rationals under multiplication, and the rigid symmetries of a polygon are one structure wearing 3 costumes. The axioms keep only what these 3 share. Associativity says that the order of grouping actions never matters. Identity and inverse say that every action is perfectly reversible. Weaken invertibility, and you fall to a monoid, counting without subtraction. The whole of part 1 is the study of what that minimal reversibility forces. This section explains what a group is at its most structural level. A group is the algebra of moves you can undo. It rests on 4 axioms and nothing else: closure, associativity, and identity, and inverses. Whatever satisfies them is a group, whether the elements are the integers under addition, the symmetries of a square, or permutations. The generative move is to forget what the objects are and keep only how they compose. Associativity says the grouping of a chain does not matter. The identity is doing nothing. The inverse is the undo. Every invertible transformation of anything forms a group. That is the entire content. And every later structure, rings, fields, modules, is this same skeleton with more operations bolted on. Drop the inverse axiom and you fall to a monoid. Subtraction on the positive numbers already escapes. This section explains why subgroups are the primitive through which a group reveals its own structure. A group learns its own structure by the smaller groups it contains. That is the whole point of studying subgroups. Instead of confronting a group as a monolith, you decompose it into the lattice of self-similar pieces nested inside it, each a subset closed under the same multiplication and inverses, hence a group in its own right, sitting inside. The primitive is inclusion as morphism. A subgroup is the group's internal image of another group, and the arrangement of all such images which already encodes most of what the group is. Everything downstream, cosets, quotients, normality, is machinery for reading that internal lattice. To know a group is to know its subgroups. This section explains what a subgroup is and why checking one takes almost no work. A subgroup is a subset that is itself a group under the ambient operation, and the chapter's whole move is that you almost never check that directly. Associativity, the identity, and the compatibility of inverses all descend for free from the parent group. The only thing restriction can break is closure. So the entire notion of satisfying the same axioms collapses into a single test. The subset must be non-empty, and for any two elements x and y, the product of x with the inverse of y must lie in H. When H is finite, closure under multiplication alone suffices. That is the generative primitive Dummett and Foote open with. To study a structure, study the sub-objects obeying its axioms, and inheritance means you verify only what the ambient object does not already guarantee. Subrings and subspaces will all repeat this exact economy. This section explains quotient groups and homomorphisms and the single identification that ties them together. A homomorphism forgets, and the quotient names exactly what it forgets. Collapse, a normal subgroup, n to a point, and its cosets become the elements of the quotient g by n, the fibers of the map that kills n. The chapter turns on one move. Kernels and normal subgroups are the same objects. So every quotient is some homomorphism's image, and every homomorphism factors through its own kernel collapse. That is the first isomorphism theorem. Normality is precisely the condition that makes coset, multiplication well-defined, the arithmetic of fibers. Everything downstream, the correspondence between subgroups of the quotient g by n and subgroups of g lying above n, is bookkeeping on that one identification. To quotient is to choose which structure to render invisible. This section explains why a homomorphism out of a group and a quotient of that group are the very same object seen from two sides. A homomorphism out of G and a quotient of G are the same object seen twice. Push G into H. The fibers, the pre-images of single points, partition G, and because the multiplication in H is well defined on them, the fibers are a group, isomorphic to the image. That group is G modulo n, where n is the fiber over the identity, the kernel. So collapsing G by a normal subgroup and mapping G structure, preservingly onto something smaller, are one operation, not two. Every kernel is normal, and every normal subgroup is a kernel. The chapter's whole arc is this equivalence. Study the maps out of G, and you have studied its quotients, which is Dummett and Foote's first taste of the idea that an object is what it does. This section explains what a group action is at its root. An action is a homomorphism from the group G to the symmetric group on the set, A, nothing more. Each group element becomes a permutation of the set, and the group law becomes composition of those permutations. The bijection between actions and such homomorphisms given in Proposition 1 is the whole content. So a group is never studied alone. You let it move a set and read its structure off the motion. The kernel is what acts invisibly. The stabilizer is what one point cannot feel. The dihedral group, D8, acting on the 4 vertices of a square, is the minimal picture. The same abstract group acting on pairs of opposite vertices acts differently, losing faithfulness. Acting on is the text's unifying verb, culminating in silo. This section explains why a group action is the same thing as a homomorphism into permutations, and how one counting equation carries the chapter toward silo. An action of G on A is nothing but a homomorphism from G to the symmetric group on A. The bijection in proposition 1 is the whole move. Acting and being represented as permutations are the same datum. Everything downstream is bookkeeping on that one map. Its kernel is where G acts trivially. Its orbits partition A. And the governing equation says that the size of the orbit of A equals the index of the stabilizer, G sub A in G, which trades a geometric count for a group index. That trade, orbit size for stabilizer index, is the engine the chapter drives towards silo. The theme is stated up front. When one object acts on another, structure flows both ways. So counting how G moves A reads back the internal architecture of G itself. This section explains how a group is read by the way it factors. The chapter turns on a single move. Given a normal piece N and a complementary piece H, the whole group is reconstructed from the 2 parts plus the gluing data. That gluing data is a homomorphism from H into the automorphism group of N, saying how H twists N. A trivial twist gives the direct product, where the parts ignore each other. A non-trivial twist gives the semi-direct product. Every distinct action manufactures a genuinely different group from the same 2 pieces. Abelian groups are the degenerate limit, where no twist is permitted. They collapse entirely into products of cyclic groups of prime order, and they are fully classified. The primitive to carry is this: structure equals pieces plus action. Counting the actions counts the groups. This section explains how 2 ways of building large groups from small ones are really a single construction with a dial. Given a normal piece, N, and a complement H, every way of assembling them into a single group is a choice of how H acts on N, a homomorphism from H to the automorphism group of N. That action is the semi-direct product. The direct product is merely its trivial setting, where H leaves N untouched and the 2 factors commute. Fix the action untouched and the 2 factors commute. The chapter's payoff cashes this out. Every finite abelian group is a direct product of cyclic groups. The pieces, plus their gluing, which here is trivial, recover the whole. This section explains how the whole chapter measures a single quantity, how far a group sits from being commutative, counted as the length of a canonical series that collapses down to the trivial group. Abelian is distance 0. For a nilpotent group, the upper central series climbs all the way to G in finitely many steps, with each successive quotient sitting in the center. For a solvable group, the derived series, built from iterated commutators, eventually dies. The spine of the chapter is one strict nested chain. Cyclic sits inside abelian. Abelian sits inside nilpotent. Nilpotent sits inside solvable, and solvable sits inside all groups. Each inclusion is a loosening bound on how much non-commutativity is allowed. The P groups anchor the low end. The class equation forces a non-trivial center, so a P group is always nilpotent, and commutativity is never wholly absent. What refuses every such series are the simple groups, the atoms that Jordan and Helder leave behind. This section explains how a single number measures the structure of a group. Structure gets measured by a ladder. Take a group, quotient out its center, then take the center of that quotient and repeat. This is the upper central series. If the climb reaches the whole group in finitely many steps, the group is nilpotent, and the number of steps is its class. That is the chapter's single move. Failure to commute becomes a number. The tower runs cyclic inside abelian inside nilpotent inside solvable inside all groups. It is one filtration graded by that number, and every containment is strict. And P groups are the atoms. Every finite P group is nilpotent because a P group's center never vanishes. So silo theory hands you nilpotent pieces from which finite groups reassemble along their prime local structure. This section explains what a ring is and the single hinge that holds it together. A ring is an abelian group that has learned to multiply. A second associative operation is bolted onto the addition by one hinge, distributivity. That hinge is the entire content. Multiplication never stands alone. It is defined by how it spreads across sums. Here is the surprise. The chapter half buries. Distributivity alone forces the addition to be commutative. Expand the product of 1 plus 1 with a plus b in two different ways, and a plus b equals b plus a drops out. So the abelian demand was never independent. Hold the integers in mind as the prototype. Everything downstream is subtraction from richest structure. Drop the requirement that non-zero elements invert, which would give you a field, keep distributivity, and the group's arithmetic survives. 0 times a equals 0, the sign rules, all of it. This section builds a ring from an abelian group by adding one more operation. Take an abelian group, teach it a second operation, and demand only that the two respect one another through a single law, distribution. That is a ring. The addition is carried over unchanged from group theory. The multiplication is associative, but otherwise unconstrained. It need not commute, need not invert, need not invert, need not invert. Everything else is downstream. That 0 times a equals 0, that negative a times b equals the negative of a b, the sign rules, none of these are axioms. All of them fall out of distribution. The chapter's quiet surprise is that even additive commutativity, once R has a 1, is not assumed but forced. The whole edifice ahead, the integers, matrices, polynomials, functions, is this one skeleton wearing different multiplications. This section explains how three classes of rings, Euclidean domains, principal ideal domains, and unique factorization domains, are one demand seen at three strengths. A single insight threads the three. They are the same demand, unique factorization, surviving the progressive amputation of the division algorithm. Euclidean means you have a size function letting you divide with remainder. Strip the algorithm, but keep its consequence, and every ideal is singly generated, which gives a principal ideal domain. Strip principal ideal domain. Strip principality, but keep its consequence, and elements still factor uniquely into irreducibles, which gives a unique factorization domain. Each class is defined by what it does, not by what it is, and the containments are strict. The polynomials with integer coefficients, the integers adjoined x, factor uniquely yet have non-principal ideals. The generative move is this. Factorization is cheaper than principality, which is cheaper than a remainder algorithm. Reeve the tower downward, and you watch one guarantee shed its scaffolding, one weakening at a time. This section explains a single move that runs through the whole chapter. Take everything that makes the integers, the ring Z, arithmetically well behaved, and dissolve it into the minimal axiom that still forces each good consequence. The tower has 3 rungs. First, a norm, together with the division algorithm, which gives a Euclidean domain. Then, the weaker condition that every ideal is principal, which gives a principal ideal domain. Then the weakest condition, that factorization into primes is unique, which gives a unique factorization domain. These are not 3 separate topics. They are one strictly nested tower. Euclidean domains sit strictly inside principal ideal domains, which sit strictly inside unique factorization domains. The implications run one way only, and each strict containment is witnessed by a ring that lives in the gap, a ring belonging to the larger class. The payoff is subsumption. The theorems about the integers proved back in the preliminaries get rederived once, abstractly, as the unique factorization case. The integer z and the polynomial ring f of x stop being special. They become 2 coordinates in the hierarchy that the axioms carve out. This section explains what happens when you adjoin a single variable to a ring and how much of the ring's arithmetic survives the step. Adjoining one indeterminate to R is the free move. The polynomial ring R adjoin X is the universal commutative R algebra on a single generator, a generator that commutes and obeys no relation. Every ring map out of it is fixed by where X lands. Evaluation and reduction modulo I are just this property firing. The chapter is then a ledger of what survives the lift. Structure climbs from coefficients to polynomials, but it drops exactly 1 rung. If R is an integral domain, then R adjoin X is an integral domain. If R is a field, R adjoin X is 1 step weaker, a Euclidean domain rather than a field. The units never grow. Read the whole chapter as this single accounting, how much of the arithmetic of R propagates upward and precisely where it degrades. This section explains what happens to a commutative ring when you adjoin one free variable, forming the polynomial ring R adjoin X. Adjoining one free variable is an endofunctor on commutative rings, and the whole chapter is a measurement of what that operation preserves. The generator satisfies no relation, so R adjoin X is the free R algebra on one element. Each property of R then either lifts intact or drops 1 rung. Being an integral domain lifts. The unit group refuses to grow. The units of R adjoin X are exactly the units of R, because X has no inverse. That same missing inverse is why a field cannot stay a field. It falls to a Euclidean domain. The primitive to carry forward is this. Passing to R, adjoin X costs 1 level of arithmetic strength, and everything downstream is bookkeeping on that cost. This section introduces module theory. Replace the field of scalars with a ring, and a vector space becomes a module, an abelian group on which a ring acts linearly, distributing over both additions. That single relaxation is the chapter's whole reason to exist. One definition is simultaneously 3 structures you already know. It is a vector space when the ring is a field. It is an abelian group when the ring is the integers, where scalar action is just repeated addition. And it is a vector space carrying a fixed linear operator when the ring is the polynomials in X over a field, with X acting as the map. The chapter sets up that unification, so later structure theorems prove once and specialize everywhere. The field was never the essential thing. The linear action was. This part explains what a module is and why one small change to the definition earns a whole chapter. A module is a vector space whose scalars forgot how to divide. Replace the field of scalars with a mere ring and keep every axiom unchanged. That single weakening is the chapter's whole reason for existing, because it collapses three objects into one. Over a field, you get vector spaces. Over the integers, you get exactly the abelian groups, since the action, n times a, is forced, so Z module and abelian group are the same word. Over a ring, R, acting on itself, the submodules become the ideals. One structure, and the book's later Galois and linear algebra machinery all runs on it. What you surrender by losing invertible scalars, guaranteed bases, and dimension is precisely what the next chapters must rebuild by hand. This section explains why a vector space is simply a module that cannot fail. Take the modules of Chapter 11, demand that the scalar ring be a field, and every pathology dissolves. Dummett and Foote make this literal. The chapter opens not with a definition, but with a dictionary. Each vector space word, subspace, dimension, linear transformation is the verbatim module definition, with the ring R promoted to a field. One consequence pays for the whole promotion. Every vector space is free. It has a basis, finite by proposition 1, arbitrary by Zorn. Freeness is exactly what generic modules lack, and once it is guaranteed, dimension becomes a complete invariant. Spaces are classified by a single cardinal. The chapter is the field theory prelude, where module theory stops being hard. This section explains what a field buys you as the coefficient ring, and why that single choice reduces an entire theory to counting. A field is the coefficient ring for which every module is free. That single hypothesis is what the whole chapter cashes out. Over a general ring, modules can fail to have a basis. They can carry torsion, they can split badly. Demand that the scalars be invertible, and all of it collapses. Every vector space has a basis. Every vector space has a basis. Every spanning set contains one, and every independent set contains one. So, the entire theory reduces to one number. Dimension is a complete invariant. Two spaces over F are isomorphic if and only if they agree on it, and a linear map is pinned by its action on a basis. The chapter is the module theory of the previous one, with the pathology deleted. What remains is counting. This section explains how one theorem about modules over a principal ideal domain generates two classical classification results at once. A finitely generated module over a principal ideal domain is a direct sum of cyclic pieces, each of the form R modulo, the ideal generated by some element A, and that decomposition is unique. The whole chapter is that single sentence. Everything else is choosing which principal ideal domain to feed it. Plug in the integers, Z, and the cyclic modules are abelian groups. The classification of finitely generated abelian groups falls out. Plug in the polynomial ring f of x, and a module is a vector space carrying one linear map T. Here, the pieces become the rational and Jordan canonical forms of T. The generative move is the ring's ideal structure. For a principal ideal domain, every ideal is a single ideal generated by one element A, and that fact dictates the module structure. Demand two generators for an ideal, and the clean decomposition dies. This section explains how a single classification theorem generates two results you first met as unrelated. A single classification does all the work. Over a principal ideal domain, every finitely generated module splits into cyclic pieces of the form R modulo. The ideal generated by A. The ideal structure of R is trivially simple, one generator per ideal, and that simplicity is exactly what pins down the decomposition, uniqueness included. The chapter's whole force is that two theorems you met as unrelated are one theorem sampled at two rings. Feed it, R equals the integers, and the cyclic modules are the integers modulo n. That gives the fundamental theorem of finitely generated abelian groups. Feed it, R equals the polynomial ring Fx, where a module is a vector space carrying one linear map, and the pieces become Fx modulo the ideal generated by F. That gives rational and Jordan canonical forms. Same engine, different R. That is the primitive to carry. This section explains what a field extension is at its structural core. A field extension, written K over F, is two things at the same time, and the whole force of the chapter is that they coincide. K is a field that contains F, and K is a vector space over F. So the question of how much larger K is collapses to a single number, the degree of K over F, which is a dimension. Adjoining a root of an irreducible polynomial, P of x is precisely quotienting the polynomial ring over F by the ideal generated by P of x. The new element's algebraic relation and the space's dimension are one and the same datum, the degree of P. Degrees multiply through towers. The degree of K over F equals the degree of K over E times the degree of E over F. So the question of whether something can be built becomes arithmetic on dimensions, which is why straight edge and compass impossibility drops out as a mere divisibility fact. This section explains why a field extension is really a piece of linear algebra. A field extension, K over F, is, before anything else, a vector space over F. That single move converts the study of fields into linear algebra. The degree of K over F, which is its dimension as a vector space, becomes the master invariant, and it multiplies cleanly up towers. The degree of K over F equals the degree of F equals the degree of K over F equals the degree of F over E times the degree of E over F. Here is the chapter's thesis. Adjoining a root alpha of an irreducible polynomial builds an extension, F adjoin alpha, that is exactly the polynomial ring. F of x modulo, the ideal generated by the minimal polynomial of alpha. The entire arithmetic of the enlarged field is coded by one minimal polynomial, and its degree is exactly the degree of F adjoin alpha over F adjoin alpha over F. So an algebraic extension element is what its minimal polynomial says it is. Solving equations becomes counting dimensions. Everything downstream, the splitting fields and Galois theory, rests on this reduction of a field to a finite dimensional linear datum over a base. This section explains how Galois theory studies a field extension through its symmetries. A field extension is studied by its symmetries, the automorphisms of the larger field that fix the smaller. The generative move is that an object acting on another exposes the structure of both. Here, the acting object is a finite group, permuting the roots of a polynomial, and what it acts on is the splitting field. The group is the invariant. Degree, subextensions. And solvability, all. Read off it. Now watch the group collapse. The automorphism group of the rationals adjoined with the square root of 2 over the rationals has order 2 because both roots, plus and minus the square root of 2, live inside the field. But the automorphism group of the rationals adjoined with the cube root of 2 over the rationals adjoined with the cube root of 2 over the rationals is trivial. The other two cube roots escaped the field, so nothing may move. Symmetry counts only roots already present. That constraint is the whole engine. This section explains how a field extension is governed by a symmetry group. A field extension carries a symmetry group, the automorphisms that fix the base, and this group knows everything the extension does. That is the whole move. You replace the question of which fields sit between f and k, and whether this polynomial can be solved by radicals with a question about a finite group. Automorphisms permute the roots of an irreducible polynomial. Each root maps to a fellow root of the same minimal polynomial, so the algebraic object is faithfully mirrored in a permutation group. The fundamental theorem makes the mirror exact, an order-reversing bijection between the intermediate fields and the subgroups. An object acting on another reveals the structure of both. Here, the acting group discretizes the continuous lattice of fields into finite combinatorics. This was Galois's own thread. Solvability of equations became solvability of groups.